Hey everyone, welcome to The Explainer. Today, we're diving into one of the most exciting shifts in modern API architecture. If you've been building systems that actually need to handle massive, enterprise-grade scale, you've definitely felt the growing pains of traditional REST architectures. So we're going to explore a really brilliant guide on how to scale those high-performance systems by making the leap from REST to a polyglot gRPC architecture. Let's get into it. So what actually happens when your systems are pushed to their absolute limits? Picture this real-world scenario, a global fleet management system. You've got thousands of vehicles constantly sending real-time telemetry, location data, and maintenance alerts. When you try to scale that from hundreds to tens of thousands of concurrent connections, traditional REST architectures just hit a brick wall. Latency spikes, servers choke, and real-time suddenly becomes sometime soon. We clearly need a completely different approach here. Here's our roadmap for the explainer today. First, we'll look beyond REST's bottlenecks. Then, we'll check out the universal gRPC blueprint. From there, we'll dive into our polyglot architecture with 3 different languages, explore unified deployment, and finally, look at the actual performance payoff.
All right, Section 1, Beyond REST's Bottlenecks.
You know, the core problem with REST is that it relies so heavily on polling. And polling is, well, it's essentially the architectural equivalent of a kid in the backseat constantly asking, are we there yet? Are we there yet? Are we there yet? It is incredibly inefficient and creates extremely chatty, heavy network communication. But on the flip side, gRPC uses HTTP2 multiplexing and native streaming. So instead of constantly asking for updates, the connection just stays open. Data streams instantly and efficiently in both directions. No more asking, just a continuous flow of information. Moving right along to Section 2, the universal gRPC blueprint. To pull off this kind of massive architectural upgrade across several different programming languages, you need a secret sauce, and that is protocol buffers, or protobufs. Think of them as our universal, contract-first source of truth. Before a single line of code is written in .NET, Node, or Python, we define exactly what the data looks like in a protobuf file. It's an ironclad contract. It ensures that no matter how diverse our tech stack is, every single service knows exactly how to communicate flawlessly with all the others. Which brings us to Section 3, 3 languages, 1 architecture. Think of this multi-language approach like assembling an elite specialist heist crew to conquer latency. Enter .NET 10. This is the muscle of our operation. When you're dealing with enterprise-grade systems where you need uncompromising speed and the ability to process a massive volume of requests in resource-constrained environments, .NET 10 is the platform you call. And the performance numbers here are literally staggering. Thanks to Native AOT, which compiles code ahead of time directly to native machine code, we're seeing cold startup times of just 25 milliseconds. Just blink and you'll miss it. And the container images, a tiny 50 megabytes. Add in a hybrid cache that boasts a 90% hit rate, and .NET 10 easily handles the heavy lifting of our fleet's core operations without even breaking a sweat. Next up in our crew, we have Node.js. Now, if .NET is the muscle, Node.js is the multitasker. In a fleet management system, remember, you've got thousands of vehicles constantly streaming real-time telemetry, while Node.js is custom-built for this exact scenario. Its secret weapon is the event-driven I/O model. Because of its non-blocking event loop, Node can easily juggle over 5,000 concurrent streams with incredibly minimal resource drag. Combine that with TypeScript for safety, Fastify for high-performance routing, and BullMQ for reliable background jobs, and Node.js just catches all that incoming vehicle data in real time without ever dropping the ball. Finally, rounding out our crew, we've got Python. Python serves as the brain of the operation. We've got the data, we're streaming it incredibly fast, but now we need to be smart about it. We need predictive maintenance and deep analytics. And this is exactly where Python shines. By hooking up a modern Python stack with TensorFlow, we can run real-time machine learning inference to predict when a vehicle might break down before it actually happens. And because we're using this highly optimized gRPC architecture, Python delivers those ML predictions with lightning-fast 5 to 10 millisecond inference times. That is real-time intelligence at scale, folks. Okay, Section 4, Unified Deployment and Observability. So we have the muscle, the multitasker, and the brain all working together. But how do we coordinate them? Well, despite using 3 totally different languages, the deployment is completely unified. We use Kubernetes with an Envoy service mesh.
Envoy is fantastic because it acts as our gRPC load balancer, handling service discovery seamlessly across the platforms. But the real hero here is OpenTelemetry. It gives us consistent, distributed tracing across .NET, Node, and Python. If a request slows down somewhere, OpenTelemetry lets us trace that exact request across all 3 languages instantly. Which brings us to my favorite part, Section 5, the performance payoff. All right, we've planned the heist, we've assembled the crew, and we've executed the plan. Let's look at the numbers. Did moving from REST to gRPC actually solve our scaling problem? The results are, honestly, incredibly satisfying. Across the board, every single language saw massive gains in throughput. Look at .NET, jumping from 20,000 requests per second under REST to a massive 50,000 requests per second under gRPC. That is a 2.5x improvement in throughput just by changing the architectural paradigm. And the good news just continues with latency. These are P99 latency numbers, meaning 99% of your requests are this fast or faster. .NET plummets from 15 milliseconds down to just 5. Node and Python see huge drops too. This means your system is scaling effortlessly, and your end users, they never, ever notice a lag. But if there is one single statistic from this entire architecture shift that truly stands out, it's this one: 50 bytes. Let me explain why this is a total mic drop moment. gRPC actually shrinks your data transfer payloads down to just 50 bytes per message. Compare that to standard REST, which often hovers around 500 bytes because of all that bulky JSON text and repetitive headers. That is an 80 to 90% reduction, literally a 10x improvement over REST. When you're streaming millions of messages from a global fleet of vehicles, reducing payload size by 10x practically eliminates network congestion altogether. It is an absolute game changer. So let's wrap this up. The true beauty of a polyglot gRPC architecture is that you don't have to compromise anymore. You get to choose the exact right tool for the job. Need maximum performance and low memory? Go with .NET 10. Need to juggle thousands of real-time concurrent streams? Node.js is your multitasker. Need deep machine learning and data pipelines? Python is ready to go. And that protocol buffer contract just holds it all together seamlessly. Which leaves us with this final, somewhat provocative thought. We've seen the painful bottlenecks of polling, and we've seen the sheer power of multiplex streaming and tiny 50-byte payloads. If REST is the past and gRPC is clearly the present, what will your next microservice be built on? It's definitely time to reevaluate our tech stacks and start building for the real-time future. Thank you so much for joining me on this explainer. I really hope this sparked some great ideas for your own architectures. Keep learning, and I'll catch you next time.